Welcome everyone. Today we are exploring the journey of language, moving from raw human speech and text into the structured mathematical data which are called tensors that machine actually process. The translation bridges chapters 3 and 4 of our curriculum. We will start by examining the language anatomy, lexicons, and linguistics before moving into the text processing phase where we clean and segment our data. From there, we translate those words into mathematical data structures like vectors and matrices. Finally, we will see how these numbers power real world applications such as calculating document similarity and building functional chatbots. Our goal is to understand how we turn word into a coordinate in a multi-dimensional space. Before we can program, we must understand the raw material. A lexicon is essentially a targeted dictionary for a specific field. Like for a medical NLP model, the lexicon is the set of medical terms used by doctors. Moving deeper, we look at graphemes. Graphemes are basically written letters and phonemes, the speech sounds. Notice the word spoon. It has 5 letters which are called graphemes, but only 4 distinct sounds. Spoon. These 4 distinct sounds are called phonemes. Finally, we have morphemes, the smallest unit of meaning. Assume a word unbreakable. It is made of 3 morphemes. The prefix is un, meaning not. The root word is break, and the suffix is able, signifying its capability. Recognizing these building blocks allows our pipeline to handle complex and variations more effectively. Once we have our text, we must break it into chunks called tokens. While a simple space split works for most of the sentences, like the capital of China, when we will break it into the tokens, we will separate the capital of China. But the real world is messy. We face challenges like apostrophes in China's capital. Similarly, whenever we speak some words like I am, or we speak some compound terms like Hong Kong, that ideally should be one token. Social media introduces further complexity with hashtags and emojis. As shown in the code here, we use specialized tools like NLTK's tweet tokenizer. It is smart enough to process emotions like smiley face, strip unnecessary social handles, and even truncate character repetitions like if someone has write down Rolex and multiple times it has write down X to normalize the vocabulary for our model. Normalization helps us reduce noise by bringing words to their root form. We have 2 main methods. The one is stemming, which is a crude process that chops off suffix. It is a fast but can result in a non-dictionary words. Like there is a word traditional, and if we are doing the process of stemming, maybe the result will be tradit, T-R-A-D-I-T. The other process is lemmatization. It is a context-aware alternative. It uses a part of speech tags to find the meaningful dictionary base or lemma, turning sometimes or, is, and am into the word be. Alongside this, we perform stop word removal to filter out high frequency words like the or an. However, be careful in question answering bots. Sometimes the words who, why, how, they are most critical signals and should never be blindly removed. So this is where text meets math. Since computers only understand numbers, we abstract text into an n-dimensional numerical space. A vector is a basically 1D array representing a single document. Each axis in that space corresponds to a unique token from our vocabulary. When we stack these vectors together, we create a matrix where each row is a document and each column is a token count. We also use one hot vectorization to represent the individual words. In a one hot vector, the entire array is a 0 except for a 1 at the specific index of that word. This transformation allows us to apply linear algebra to human language. How do we represent word importance? The bag of word approach simply counts frequencies. Its flaw is that it gives too much weight to common low information words. So to solve this problem, we use TF-IDF, that is called term frequency inverse document frequency. TF basically counts how often a word appears in a specific document, while IDF penalizes words that appears too frequently across the entire collection. So by multiplying these, TF-IDF scales up rare, highly informative words like specific nouns and suppress common noise. This ensures our mathematical representation actually captures the unique signal of each document. Once our documents are vectors, we can calculate how similar they are by measuring the angle between them. This is called cosine similarity. If two vectors point in the same direction, their cosine value is +1, meaning they are perfectly similar. If they are exactly opposite, the value will be -1, as you can see in the formula and code. We calculate the dot product of vectors a and b divided by the product of their magnitudes. This is a standard way to find overlapping meanings without being distracted by document length, as it measures the direction of the intent rather than just the raw count. Finally, we bring everything together to build a basic chatbot. Using a dataset like Amazon's electronics question and answers, we follow a simple 5-step engine. First, we set up our corpus and vectorize all stored questions using TF-IDF approach. When a user enters a query, we vectorize that input too. We then use cosine similarity to find the stored question with the minimum angle to the user's input. If the similarity is strong enough, the bot returns the corresponding answer. This simple implementation proves that by identifying morphemes and applying matrix math, we can empower computers to find human answers hidden in raw text. I encourage you to explore the answers which are given under the module section and specifically practice this chatbot code. Thank you.